Today we're going to talk about aluminum and all the other metals that we haven't yet. We've already talked about steel and cast irons, which are very important in our society. But now we're going to talk about the other metals. So, aluminum is the third most abundant element. Al2O3 is the composition of what you find in the earth typically, but it's usually mixed in with a bunch of other things, so they have to somehow separate it. Approximately a third the density of steel, and it's more expensive than steel. So one of the things that Ford did was to try to put more aluminum. They put an aluminum body on the Ford F-150 truck, and that's great. But the problem is that it's more difficult to weld it and repair it, and also it costs more because the energy it takes to make aluminum is way more than the energy it takes to make steel. So the difference in price, I can't remember what it was, like about $1,000 or something like that, or $1,500. That is due to the increased amount of energy it takes to get the aluminum out of its ore, and then also because the vehicles are, a little harder to make, and that they don't make many aluminum vehicles. My Land Rover, it was aluminum back in the old days, but it was pretty much pop riveted together like an airplane. So it's easy to machine, corrosion resistant, and when it says some alloys are corrosion resistant, and the deal is that certain alloying elements will increase the or decrease the corrosion resistance, like copper. So certain alloys are good, some are not, and there's coatings we can do and things like that. So it's got good formability, or relatively good formability, conducts heat and electricity, and its melting point is about 1220 for pure. When we're making castings, the aluminum we have in the lab, alloy 356, I believe that it becomes completely liquid about 1050 degrees Fahrenheit. So got a relatively low melting temperature compared to steel and cast irons and things like that. Steel typically pour at 2800 or something like that Fahrenheit, and then cast irons maybe about 23, 24, 2500 Fahrenheit. So okay, so let's move on here. How do we get the aluminum out of its ore? Now, I'm not going to test you on the exact process that goes through here, but this process is where we take the ore and purify it to pure alumina. Okay, so bauxite is the ore, and alumina, again, is the thing we're after, because we need pure aluminum oxide for the next step, and we'll talk about that in a minute. So bauxite ore comes from Jamaica, and if you've ever watched, it's one of the James Bond movies, the old ones with Sean Connery, is in Jamaica, and they're running around in this doctor no, but they're running around in a bauxite processing facility. Oregon, Washington, Arkansas, Australia has lots of it. But basically we need to get it from this. It's mixed up with silica and other things that are in the ground, and we need to purify it to pure alumina. So how do we do that? We look carefully at the schematic here. First thing we got to do is get the bauxite and crush it up in a rod mill. We mix it with some lime, and this is a liquid process. And then it goes through several purification steps. One of them being precipitation, which means that we dissolve it and then precipitate the aluminum oxide back out of it. And then it is thickened. In other words, we try to filter it or get the liquid out of it. And then we calcine it, which means we dry it back out. So it's a liquid process, and then it's calcined and dried back out at the end. one thing you may not know is that all those semi-precious stones like rubies and sapphires and other things like that are made out of aluminum oxide, crystalline aluminum oxide, and it's 9 on Mohs hardness scale, 10 being diamond. So a lot of times we use aluminum oxide for sandpaper and grinding stuff, grinding wheels. Okay, so how do we get the alumina with an A on the end to aluminum metal? Okay, so what we need to do is we need to steal the oxygen from the aluminum. If you see here Al2O3, we need to steal away that oxygen off of that. So how do we do that? The problem is that aluminum is one of the most stable compounds, and so in order to steal the oxygen away from it, it takes a lot of energy, and it actually took a special process. And what's kind of interesting is that Napoleon was very wealthy, of course, and when he was in power, he had aluminum tableware. And the reason was that at that point, aluminum was the most expensive metal on the planet. So back then, they didn't have the process they have now to make aluminum from alumina. So we have a mass production process, but it still takes a ton of energy. Not really a ton, but okay. So what do? We take, if we look carefully here, we have alumina powder being added to this big furnace thing. Okay, I'll put a link to some videos on this process in this assignment here. But we have a carbon anode. Okay, so that's a positive. And then we have a negative, which is the carbon lining. So basically everything in this furnace is made out of carbon. Why? Because carbon doesn't dissolve. It can withstand high temperatures, conduct electricity, and it doesn't dissolve in aluminum. Aluminum likes to dissolve iron and other things that you put into it. So what we're going to do is we're going to pass a current through, what is this? This liquid here is a salt. Now imagine table salt, the solid white stuff that you have on the table. That is sodium chloride. Okay, so aluminum fluoride is a salt, and it's called it's called cryolite. It's sodium aluminum fluoride is what it is. Okay, so sodium aluminum fluoride is a salt. You take that and you heat it up until it melts. Okay, now this is above the melting temperature of aluminum. And so it stays liquid because this process creates heat. Okay, but we have these things called the Hall cell. Well, why do we call them Hall cells? Because a person named Hall was the American person that invented this. Now, there's another guy named Héroult over in France that invented it at the same time. So they call this the Hall-Héroult process, which over here we call it the Hall process because we don't want to give the French any kind of credit for it. So we have the carbon anode, the positive. It reacts with the alumina and the molten cryolite. And essentially what goes on here is the cryolite is a catalyst to reaction. And that was the key, that this molten cryolite was in there. And for some reason, it will allow the alumina, the oxygen in alumina, to combine with the carbon on this anode, and it makes carbon dioxide. And then the molten aluminum that's created sinks to the bottom. So this happens at high temperatures. Eventually they come along and they siphon off the molten aluminum into the ladle over here, and then they cast it into ingots. When I was working in South Africa at the foundry, we actually made the siphon tubes for the aluminum smelters over there, and those siphon tubes would eventually wear out. They would dissolve in the molten aluminum slowly, and so they'd have to keep making more of them. So it's a good business to be in. Okay, so let's talk about what happens after this now. So now we have an ingot. We've cast it into an ingot of some sort in this casting machine, and we'll see that in the video as well. So what happens now? Okay, so this is called, like, sometimes they call it virgin metal or virgin aluminum, where it doesn't have any impurities in it yet. And so when we're recycling metals, the big risk is that the recycled materials that you're bringing in are not of the same composition as what you want. So that's a problem. So how do we get around that? Well, we sort really well at the junkyard. Okay, so when you take aluminum into the junkyard, that's why the person there is real picky about, what you have there in your bucket is all the same type of material, or they'll sort it out, or they'll call it mixed, and then they'll have to go and sort it out later on. So we don't want contaminants. Now, a contaminant might be if we're trying to make the 356 alloy that we use in our casting portion of this class. That has some silicon and some magnesium in it, so very specific amounts. And if we have some copper contamination, let's say, or too much magnesium, or manganese, or some other element in there that's detrimental, iron is a big one. If you had a bunch of iron in there, it will make the mechanical properties much lower than they would normally be. So most of the times we're interested in making sure that we have a high strength material. So the virgin material goes in, and then that can dilute out some of those, let's say, non-desirable elements. So, the solution to pollution is dilution, right? So we have these elements that we don't want in there, but what we can do is just get them down to a low enough level that they're tolerable. They're within the boundaries of the alloy that we're trying to produce, and then we can recycle this material infinitely. If we paid closer attention to that composition, then we would be much better at recycling. So that has to be like when you recycle a car. Well, if you knew that certain components on the car were made out of this alloy, then you could, if you took the car apart somehow, then you could save those easier. Okay, so we have alloying materials, aluminum ingot, and scrap. Okay, so we're going to mix those together in a proper proportions in this big furnace here. They call it an alloying furnace or a reverberatory furnace. And these are huge. These are like the size of swimming pools, like a big, sometimes, I don't know, maybe like half an Olympic swimming pool or something like that. And then they have big, like, natural gas burners over the top of them, and they're about 3 or 4 foot deep. And then the alloyed aluminum is taken into a casting unit. They will cast it actually down into the floor usually. It's like a continuous casting machine we talked about for steel, but it's for aluminum, and they don't do it continuously. They do it in, let's say, 10, 12, 16, feet or something like that of length. Okay, so then it comes out and it goes into a furnace so that the whole bar is uniform in temperature, and then it goes to a hot rolling mill. So what's going on there is it's going to, when it's hot, it can be more easily reduced in cross-section. And then we go to different types of furnaces here. We could go to a horizontal heat treating furnace. So if we get it to the right dimensions down here, like plate, maybe it's 1 inch thicker or something like that, we would go through a heat treating furnace where we would actually make it stronger. And then we would do some finishing operations. We go through another heat treatment where it completes the heat treatment. And then we have our plate, so 1/4 inch and thicker, okay? If we're trying to make sheet or thinner materials, strip, then it goes through an annealing furnace, which gets it nice and soft. It goes through a cold rolling process, gets to the right dimension, and then it goes through a heat treatment furnace. And you can see they're like rolls here. So it unrolls from one and goes onto a roll over on the other side. So as we go thinner and thinner, it acts more like aluminum foil or something like that. But Anything smaller than a 1/4 inch is considered sheet instead of plate. Okay, so a lot of times if it was on a round thing, they'll have to flatten it back out through some rollers, and then they'll shear it off to lengths, or they'll supply it in a big coil. Either way, so about 6/1000 of an inch thick to just under a 1/4 inch. Okay, so that's a lot to know, but that's generally the process. It's very similar to steel making, rolling it into plates or whatever shapes you need. Now, aluminum does have the ability to be shaped a different way, and it's called extrusion, and I'll throw a video of that up as well. Okay, so we have aluminum alloys being produced in a furnace. The ingots are cast, heated uniformly, and then rolled hot, and then we take it down to whatever dimensions we need at that point. This is mostly for flat product, okay, for flat plate and sheet. If we're trying to make other shapes, again, we'll make them by usually by extrusion. Okay, so how do we designate aluminum alloys? Okay, so you may have had some experience with this stuff before. If you're into cars or something like that, you might see that a really high-end part might be a 6000, like 6061 or something like that. So each one of these alloy designations would be either for pure aluminum, for copper, manganese, silicon, all these different alloying elements are the primary alloying elements. Now, as we go up this list, like the 7000 series is the strongest, okay? But these are used for different things. The 3000 series would be like your diamond plate, the real shiny stuff that you weld bumpers out of, or really nice toolboxes. The 2000 series is very strong, but it's not very corrosion resistant. We don't use it much anymore. This, like the old World War II airplanes, were usually a 2000 series. But if we have some real high strength applications, we might put this 2000 series in there. We just got to make sure that we keep it from corroding in different ways. If I'm making wires to conduct electricity, or maybe I want to make a heat exchanger, I might make it out of a 1000 series, which is nearly pure aluminum. And then 4000 I don't see much. The 5000 series is usually stuff for like shipbuilding. So if you're going to make a hull out of an alloy, it might be a 5000 series. And then 6000, 60, these alloys are very popular. So this is typically what you would get if you got some, let's say run-of-the-mill type aluminum that you're going to machine into some shape. It would be this 6000 series. Okay, most of these alloys are heat treated, but not all of them. This 5000 series is not heat treated in order to get its maximum properties, whereas most of the other ones are. The pure aluminum really can't be strengthened much except by cold working. Okay, remember that when we cold work something, we increase the mechanical properties slightly. So here's some typical alloys of aluminum. 1100 is pure aluminum. The 2024 would be like a structural aluminum that you would use for high strength applications. But the 6061 is pretty strong, good all around alloy. We can weld it. It's got high tensile strength. It's pretty corrosion resistant. It does need to be heat treated in order to get that high tensile strength. And so you have to, if you're going to weld it, you got to weld it first and then heat treat it. And the 7000 series is the highest strength stuff. Aircraft, a lot of components in the aircraft. Usually they make a big block of it and machine the components out of it. It's very wasteful, but it's one of the ways to do things. That's why our airplanes cost so much. And then the cast aluminum alloys have a 3-digit system, and 356 again is the alloy we use, and that is like the 6061 in that it has silicon and magnesium. Okay, so when you buy aluminum, you have to say, well, I want this type of aluminum, the 6000, let's say 6061, but then what kind of condition? Remember that the history of the metal is very important. So what kind of condition do you want that metal to be in when you get it? So you pretty much want it to be in a high strength one, typically, for if you're going to machine it or if you're going to do something like that. But if we wanted to form it, we wanted to forge it or do something with it, maybe we want to get it in the annealed condition. Okay, so annealed means softened. And so if we look at this chart here, we got F is as fabricated. So the 6061 would have a dash, and then it would have some, letters after it. So T6, if we look at that, solution heat treated and artificially aged. That's typically what you'll get. Okay, 6061 T6. But if you saw something like 6061 O, it means it's annealed, and it says for wrought alloys only, which means that wrought means that's rolled or formed, whereas cast is a different thing. Okay, so wrought would mean it's cast first and then it's rolled or something else been done to it. Okay, so if it would be 6061-O, then we would know it is definitely annealed. Okay. H stands for strain hardened. Again, wrought alloys only. This means that you've taken the thing and put it through a rolling mill or something like that while it was cold, and then you get it partially strain hardened. Okay, so there's a bunch of different. So just remember, H stands for strain hardened, and then T stands for thermally treated. You might think that H would stand for heat treated, but it doesn't. It stands for strain hardened. Okay, and so there's a bunch of different things, but just remember the T6 one is the solution treated and artificially aged. What does that mean, actually? Okay, so when we make some castings in the lab and we want to heat treat them, what we do is we take them and we put them just under the melting temperature of the aluminum, which is about 1,000 degrees. Remember, 1,050 or so is where our aluminum melts. So we put it at 1,000 degrees, maybe sometimes up to 12 hours. And there's an internal change that's occurring in the aluminum. Things are dissolving, kind of like when you guys are doing your screwdriver tips, that they got to be in there for 20 minutes at a certain temperature. And if you don't have them at that time and temperature, the stuff that's supposed to dissolve doesn't dissolve. Now, this is weird. You're thinking about something that's dissolving in a solid. So yes, chemical reactions occur in solids. You're normally used to seeing them in liquids. You put sugar in water, and it takes a while for that to dissolve. Okay, there are chemicals that are already in, or elements that are already in the alloy, that when you heat them up, they'll dissolve. Okay, for 6061 aluminum, it's magnesium and silicon. Both of those go in a solution at that temperature over 6 to 12 hours, something like that, and then we quench it to room temperature, which now we have a supersaturated solution of silicon and magnesium in aluminum. And then if we heat it to a lower temperature and allow the atoms to move around a little bit more, they combine and form little particles that tend to make the metal more stiff. And we'll go into what those mechanisms are later in the class. But understanding this is the key to making the right decisions when it comes to deciding what type of heat treatment to do for a metal, or just understanding what's happening in some process that you're doing. Why are our parts all coming out soft? Well, let's go and look at the temperature that this furnace is at. Maybe you're doing your heat treatment at the wrong temperature or something like that. Or an operator changed something and now things aren't coming out right. So your job may be to be the kind of the detective and figure out what's going on, because many of you end up as process engineers, and a process engineer, that's kind of what they do. Okay, so kind of know some of these, like T6 is important. Know that H is strain hardened, O is annealed or something like that. That would be good things to know. Okay, so now we talked about aluminum, and aluminum is very important. I would say, you have cast iron and steels being, the most prevalent, and then we see a lot of aluminum now on cars, even trying to lighten the cars. And it kind of annoys me when they say lightweight alloy. Well, it's got a lower density, but that's not what we're talking about. We're talking about the strength to weight ratio. So how strong is it for how much material I have to use? And some aluminums do beat some steels in the strength to weight ratio. And some steels beat many aluminums in the strength to weight ratio. So both of those materials are competing. The problem is that aluminum is more expensive. So if you want to use it on your car, it's also a problem from the standpoint when you put aluminum next to iron, you get galvanic corrosion. Okay, so that means that the two metals kind of like form a battery. And if you have liquids around, so we have to keep the metals separated from each other. Well, that's kind of a pain. My wife is a lifesaver. She actually works at a life-saving station here in Madison. She drives a 31-foot motorboat around. They look over the lake, and if someone's in trouble, they go out with this 31-foot motorboat. They just bought a brand new one, and it's made out of aluminum. And there's some fittings that they put onto the aluminum hull that were, I think they were stainless steel, and there was corrosion happening all around where those fittings were connected to the boat, because those two dissimilar metals were creating galvanic corrosion. So what they had to do, and what they should have done, is they actually put little pieces of plastic in the holes where they go through the hull, so that we don't have that electrical contact between the two materials. So that can be a problem, especially in salt water, and this is even a freshwater situation where they were having major corrosion after just a few weeks of using the boat. Okay, so copper base. Copper base alloys were a lot more prevalent in the past, but they're still used a fair amount for their special purposes. They're very good at corrosion resistance, and they're good conductors as well. Sometimes we use them for switch gears, where you actually have a switch and it has certain types of copper-based alloys in there, so that there's arcing or something like that when the switch flips. Or sometimes we even make springs out of copper, certain copper alloys. But generally we have copper. Bronze is copper and tin, and brass is copper and zinc. So that's the definition. Now, there's many exceptions to this, just like the English language, okay? Usually the melting point for copper is around 2,000, but it's lower for the alloys. So you might pour some brasses at about 1,500 degrees, but usually more like 1,700 degrees, somewhere in there. Okay. So here's some examples of brass. These are brass cartridges, are formed to that shape. These are machined. They probably extrude the brass, and then they machine it. And then here is a casting of some sort. So this could be a die casting, where I actually use a metal mold, because you can make lots and lots of parts off of one mold then. Okay. So those are, and you can tell it's, how do you know it's brass? Well, it's usually a little bit lighter, like a more silvery, I guess, or like a lighter color, not as copper colored. But there's a lot of different alloys. Now these ones, cartridge brass is 70% copper, 30% zinc, somewhere around there. Okay. Bronze, it's copper and tin. Okay, you can see it's a little bit more red, typically, but some bronzes can be the same color as brasses. So, depending on the amount of different elements in there. But again, copper and tin. Bells are one of the few purely copper tin alloys. So bells are 20% tin, 80% copper. And then here we have some bronze bushings, which those tend to be maybe like 10% tin. So there's certain alloys that you use bronze for. One of them might be, I don't know if you've ever seen this in your car, these little bushings that go in motors and stuff like that, but on your transmission, the pilot bearing on a transmission, the older cars had these bronze bushings, and they call them oil light bushings. It's essentially bronze that's actually, it's not a casting or anything, it's particles of bronze that are compressed together, and it's kind of a porous bronze, and they inject under high pressure. They impregnate it with oil, so they call it an oil light bushing. So it's actually got oil in the bronze, and it's actually a very hard material too. So my son's Jeep had a problem, and the transmission, the nose of the transmission, the pilot was scored, so we ground the surface, but it was a non-standard size, so we machined a bronze bushing to go in there for the pilot bearing instead of a roller bearings, and it's still working fine. Okay, so here is an example of where there's exceptions to the rule. Leaded red brass. This is what used to be used for almost every faucet in this country, and just about anything that touched drinking water. Now, you might say, well, why would you put lead in it? Well, that's the problem right now. They're trying to get rid of this lead because small amounts of it leach out into the water. And so we were, but I don't know if you know this, but Platteville was a lead mining town, and most of the pipes in the streets are actually, some of them are still lead. I'm serious. The actual pipes themselves are lead. We still have pipes in Madison that are made out of lead. Okay, so how can that work? We have such hard water that you get a layer of calcium deposits on the inside of it very quickly, and therefore you're not getting much of that lead when you drink it. Okay, so they're slowly replacing all the pipes, and then some of the valves that they're putting in still have a little bit of lead in it. Why would we put lead in it? Well, a bunch of reasons. Okay, lead is awesome at plugging up the last areas to cool in the casting. So what happens is otherwise the casting may be porous and it will leak. Okay, so the lead plugs the holes and so it doesn't leak. Now I want you also notice something, that it is 85 copper, 5 lead, 5 zinc, and 5 tin. So is this brass or bronze? It has the same amount of tin and zinc in it. Well, for some reason they call it leaded red brass. Okay, so not sure how they came up with that, but it's called 85-3-5 because 85, 5, 5, and 5. So now what they're doing is they're replacing this lead with some bismuth, but it's not as easy to cast because the lead doesn't anymore plug up all those little holes, and we get more leaking castings. So the people that cast these valves now have to be more careful about how they do their casting operations. A.Y. McDonald right in Dubuque nearby, we have a couple of former students working there. One just got a job there recently, actually 2 of them. And they switched over to non-leaded about 10 years ago, and they had a lot of problems. They had to buy some software that models what happens when the metal cools, because making leaded red brass castings is super easy. Making unleaded ones is not. Okay, so that's a little side deal. So pretty much any faucet that you have is some variant of this in the old days, and then they have some new ones out now that have much higher zinc contents and a bunch of proprietary ones now that people are using. They have no lead in them. Okay, what temperature do other metals melt at? Okay, so solder, 50-50 solder, we're talking 400 Fahrenheit. Pewter, 420. In fact, this is kind of an interesting thing. I want to do some heat treatment, and I'm going to use pewter, which melts at 420, and some types of pewter actually lower than that. So I actually want to quench knives into pewter or tin, which melts at like 450. Okay? Then Babbitt, some of these we're going to talk about what the heck they are. Lead, 621. Zinc, magnesium, 1200. Aluminum, 1200. Okay, bronze, 16. Okay, which bronze? I don't know. Brass, 1700. Silver, 1700. Okay, gold, we're getting up to 2000 here. Cast iron, 2200. Beryllium 2323. Now beryllium is a really light material. We're going to talk about that too. It's like aluminum, except for the fact that it's poisonous and really expensive. Okay, steel, 2,500. More like 2,700. Nickel, wrought iron, 2,700. Titanium, 3,000. Wow, that's really hot. Tungsten, 6,000. Okay, so we have to deal with these temperatures. We don't have anything that we can melt tungsten in that won't melt also. Okay, so tungsten is a higher melting temperature than most things we have that we can melt in. Aluminum oxide is really good refractory. In other words, it's like a ceramic that we can melt metal in, right? And we have a furnace that we melt metal in that is, I think it's 95% alumina lining. It goes to about 3,200 degrees. So you can see that we couldn't melt titanium in it. The other thing is that titanium will steal the oxygen away from the aluminum oxide, and we'll have aluminum and titanium dioxide, because titanium is more stable than aluminum is. So let's talk about these other materials. Okay, Babbitt. Babbitt's pretty cool stuff. It's the old-fashioned bearing material. So if you have really old machine tools or really old saws or something like that, they'll have Babbitt bearings. If you use steam engines or any really old car engines, they'll have Babbitt bearings. It's a low-temperature material that's cast into a shape and then machined to its final dimensions. So here's an example. You could buy for old-fashioned Fords. This is, I don't know if that's a Model T. You could buy these Babbitt bearings, and it says in here, it says that they were. I thought it says. Yeah, I thought they were die cast or something like that. It said somewhere on this, but anyway. Oh yeah, right there, die cast Ford bearings, right? Okay, so this would go in your connecting rods. Okay. That's a small engine. This is, they're putting in a Babbitt bearing for a crankshaft for the world's largest diesel engine. So I forget all the specifications on it. It's completely ridiculous. It's something like, it's 100 RPM and it's like 100,000 horsepower or something like that. So the crankshaft is huge. The pistons are like 5 feet in diameter, 6 feet in diameter. I forget how many cylinders. It's like 12 or 16 or something like that. So Babbitt, I've actually made Babbitt bearings for my buddy's MG. He's got a 1931 MG that he races, and so we've actually cast. There's a steel liner, so we actually cast a Babbitt bearing inside of it. And what you do, it's kind of like solder because it's got tin and some other materials in it. I never really said what's in it, but lead, tin, copper, antimony. It's very low temperatures, and so you have these mixtures. There's different kinds you can buy, and then the idea is to get them to stick to the steel. If you have some of them actually have like removable ones, so you can like slide it in there. So what you do is you cast it, but you have to get it fluxed really good so that you get a metallurgical bond. So it's almost like soldered to that steel bushing. So it's really tricky to do. You have to tin it. You have to kind of like get a coating of tin on the surface and then cast it. Okay, so beryllium. This is cool stuff. It was used for the space program. Very expensive, lightweight, melts at like 2,000 something degrees. They are starting to cast this to some extent, but the dust is toxic, and if you don't want to eat it either. If you look at where it is, it's right next to lithium, okay, and lighter than magnesium, okay. So this is really light stuff, and it's very strong. So why don't we use it more? Well, it's expensive and it's poisonous. um, in your book, it talks about these cast alloys, and I was trying to come up with some applications of this because it's not used all that much anymore. But in the old days, before they had cemented tungsten carbide cutting tools, the cast alloys were basically certain elements. It's like you would have cobalt, chrome, and high amounts of all these things, and it's not a steel-based alloy. So the primary, like each one would be like 20% of each one of these. I don't know if I have a composition on them, but and they have things like trade names like stellite. But it's not used much anymore. But we still, once in a while, will use it. This is a company in Valparaiso, Indiana. It's a company called Urschel Labs. And they have cornered the market on any type of food cutting or food processing. So like Frito-Lay's potato chips. This one here, I believe, makes French fries. So how it works is you put potatoes in here, and this thing's spinning around really fast, and centrifugal force pushes the potatoes through this thing. So they're just fed into this tube, and then centrifugal force, the fries fly off the outside of it, and they're caught somehow, and then taken and processed further. So we actually saw these being cast down in Indiana a couple years back. And that's so the insides of those are sharpened edges. You can't quite see them, but they take this and they sharpen their cutting edges on the front edge of each one of these things. So, what about gold? Gold is pretty cool stuff. Very beautiful in color. It's very malleable. In other words, we can keep on hammering it and make it into almost an atomic layer of metal. And they use it for gold foil, things like that. It's great at, I don't know, they used it on the face shields for the astronauts. It doesn't corrode. So like silver and other elements, it's found naturally in nature because it's so corrosion resistant. It basically doesn't corrode at all. It can be alloyed with copper. If you alloy it with copper, you can have like rose gold. You can have, if you do it with nickel, you have white gold, and sometimes they add a little bit of silver to it for different types of gold. So, but it's mostly used in jewelry and in things that you don't want to have corrosion. Okay, even electrical contacts. Silver's got the highest, by the way, silver has, and we're going to talk about that in a second, but silver has the highest conductivity, but it does oxidize. So we could have silver and then maybe gold plate it so that the contacts don't oxidize. What do we use lead for? It's used for lots of things. Although we found out that it is toxic. So, I played with lead soldiers when I was a kid. I had a little lead casting set, and my mom always told me to wash my hands or anything, but I never did. So I probably ate a lot of lead. Good thing it has never affected me. We'll see. Very high density. We use it for ballast a lot of times for things, in ships and things like that down on the keels, or it's low temperature melting point, so you can pour it at low temperatures. Maybe make a steel shell and you pour the lead inside of it. For batteries, all the plates in the batteries and the little knobs on them and everything. Funny story, I did a court case a while back for a company in Minnesota, and the name of the company is, what is it? Water Gremlins, and they make little parts for, they actually make little sinkers and stuff like that, but they also make parts for batteries, okay? And they die cast them. Those are die casts. So let's go back to the lead thing here. It used to be used in solder, but now they've substituted other things like bismuth in the solder. Why? Because, again, lead was poisonous. And then if you're soldering pipes together in your house, you could get small amounts of lead in there. Although the lead solder was much better. One of the problems they're having with the non-lead solders is that lead, because it's got such a low melting temperature, and because of the crystal structure of it, if you take lead and you bend it back and forth a million times, it will never work harden, because you're above the recrystallization. In other words, it's always annealing itself because it's got such a low melting temperature. When you bend it, it's like you're bending it really hot, right? So people use them for duck decoys, I guess, pure lead. They can bend these little things back and forth. I don't know exactly what the deal is, but I know I had a lot of students that wanted pure lead. And if they're not pure lead, then they'll fatigue over time. So when you make solder that does not have lead in it, when your circuit boards are bouncing as they go down the road in your car and stuff like that, they'll start to work harden. And eventually those circuits will crack. And now you don't have an electrical contact. So the old leaded solders are really good. And I think they still use them in the military because they don't want the stuff to fail. Leaded paint, what's the deal with that? Well, lead oxide is white. And so they would have, paint the houses with lead oxide, and that would make the house white, or it'd be like a light color in your house. And so if you got a house older than 1970, when they want to paint it, they won't sand or anything, because the small particles of it, you ingest it or breathe it, you get lead poisoning. Okay, so lead oxide is actually slightly sweet tasting. So when you put it on windowsills and stuff like that, kids would love to chew the windowsills because it tasted sweet. And then they would get lead poisoning. And so it's not a good thing. They used to make cribs and stuff. Painted the crib with like leaded paint. So why are these kids all getting lead poisoning? Because it was in the paint. So now what they do for paint is they use, for white pigment, they use titanium dioxide. So that's no longer we're using lead. So it's toxic. So if you had, I don't know what the amounts are, but it doesn't take much lead to get lead poisoning. And for young people, it's really bad. So make sure when you have kids that if you do have kids, that you pay attention to that. I think Henry was having problems at his house. It was flaking off the ceiling. He's got a really old house, and that those little particles were getting into the clothing. It was in the washing area, and so they had to test everyone, and they did find lead in the house, so they had to go and take all the lead out, and special abatement kind of stuff has to be done that way. Okay. So it can be a problem. Magnesium and alloys. So I don't know if you ever heard the expression mag rims for your cars. They used to refer to magnesium rims. They used to put them on cars because they're lightweight. So for like race cars, they would have these magnesium rims. I don't know why they don't do it anymore, besides the fact that it's really kind of a pain in the ass to cast magnesium, because it can ignite and burn your foundry down. So high strength to weight ratio, relatively expensive. And then, there's not many of these mag rims around anymore, because people tend to like the old rims that are dented or whatever. They'll throw them in a fire, and then it makes this really, really bright fire for a long period of time. But it burns at like 4,000 degrees. So you have to be really careful what you're doing, because you can't put it out. And if you put water on a magnesium fire, what happens? Now let's think about that. H2O. Magnesium likes the oxygen in water more than hydrogen does, so it steals the oxygen from the hydrogen, and now we have two fires. We have the magnesium burning more because it just stole some oxygen, and we have hydrogen, which kind of comes off the fire and finds more oxygen outside the fire, and you just basically, made two fires. So people put sand on it. They have special foams and stuff you can put on magnesium. There's special stuff that you want to do. If you take if you're a firefighter and you take a hose and you blast a magnesium fire, you're probably going to die. Many firefighters have died from that. Okay, nickel-based alloys. So what are these? These are really high temperature alloys we use for jet engines typically. They're super expensive. Nickel is expensive. So what we mean by nickel-based is that nickel makes up the more than 50% of that alloy. Okay, so it's got nickel. Let's see what else we have. I think somewhere I talk about it. Maybe not, but nickel, cobalt, really molybdenum, really expensive alloys go into this stuff. So Inconel, Hastelloy, Haynes, these are all proprietary alloys that go into parts of a jet engine. Here it shows a cross-section of a modern jet engine. It's a turbofan engine. So I don't know if you know this, but the old-fashioned airplanes used to go faster than the new airplanes because it's more efficient if you have a turbofan instead of a turbojet. So we're not using the thrust coming out of the back of the engine so much. We're using this bypass fan. So essentially it's a really fancy propeller. It's a ducted fan that goes relatively quickly. These blades here are going to be titanium, but a lot of the rest of it is nickel alloys, especially as we go toward the back of a jet engine. So I don't know if you know how a jet engine works, but up here we have some sort of combustion chamber. We have a compressor, so we're compressing air in the front end. Then we combust it with fuel, and then coming out the back end, the combustion chamber is nickel alloys in here. As we come out the back end, it makes a turbine turn. That turbine is connected to the fan on the front all the way through the shaft. And so it's like a turbocharger, essentially. We compress the air on the front end, we burn it, we add fuel to it, and we burn it on the back end. It's almost like a combustion engine, except it's continuous instead of like, a internal combustion engine is like sporadic. You have it goes through 4 strokes, and then it fires. This thing is firing continuously, and it's very efficient. Okay, so many parts on that. Why are they nickel-based alloys? They call them super alloys sometimes. Why are they? Because think about this. This engine turns sometimes in the neighborhood of 30,000 RPM, 40,000 RPM, really, really fast. So all the stuff in here wants to fly off. So it's at high temperatures, maybe over 1,000 degrees Fahrenheit, maybe 1,500, 1,700 degrees Fahrenheit inside here. And so most materials at those temperatures will start to stretch. They call it creeping. If your fan has a fan shroud on it, and there's only a few thousandths of an inch of clearance around there, otherwise we could blow by, and that fan starts to get bigger in diameter, what happens? Well, it starts abrading the sides of the engine. And they're made to do that to a point. Then you have to replace the seals on it. So essentially, the compressor, or not the compressor, but the turbine ring is getting bigger and bigger. Maybe over, 10,000, 20,000 hours that the airplane is flying. It's under high temperatures and high stresses in the outward direction because the thing's spinning, right? Centrifugal force wants to make it bigger, and it does get bigger. And eventually, they know that at that temperature and for, 20,000 hours of flight, I don't even know what the numbers are, you have to replace that compressor or that turbine. And they're very expensive, by the way. And so that's why airplanes are so expensive. They have to go for all this routine maintenance. That's because these parts cannot withstand those temperatures for infinite amount of time. Also, there's corrosion inside the engine as well. It's high temperatures, you get high temperature corrosion. Okay, let's go back here. Pewter is made out of tin and other elements such as antimony and copper, just making it a little bit stronger. Sometimes lead. You don't want to have lead in like this drinking mug here, though. But pewter is used for a lot of really ornate little doodads. Um, you know, you can get a little John Deere mug like this even nowadays. By the way, a lot of this pewter stuff is made in Madison. There's a company that does. They did all the little miniatures for Dungeons and Dragons back in the old days, and even now they make many of the Warhammer and all these things. They make the little figurines, the ones that are metal. So even on resin, they're a pretty cool company. They also make a lot of Disney stuff. Artists will make something for Disney. They make the originals, and then they send that over to China to make all the production stuff. Okay, silver. What are we doing with silver? Yeah, well, it's a really good conductor of electricity. It can be used in bearings. Some of the best bearings are silver. Of course, they're very expensive, but it's a really good bearing material. And then just so you know, sterling silver, if you've seen something like, everyone used to have sterling silver, like a tea set or something like that. No one does that anymore, but maybe you got one from your grandma or something like that. Sterling silver is something like 91% silver, and the rest is copper and something else. I forget what it is. But mostly copper and silver is what sterling is. Okay. Now, tin is a relatively high density, low melting temperature material. It's very corrosion resistant, so a lot of times we'll use it in tin cans. So we coat the inside of a piece of steel with tin. Tin cans are made out of steel. So remember that. Tin cans are made out of steel. They only say tin because they have a tin coating on them. Okay? It's also not used for aluminum for foil anymore. They used to, but it's aluminum foil now. So tin is very misunderstood. I remember I saw a garbage, a big dumpster, and literally it was labeled tin, and it was full of stuff. And if that dumpster was, tin is like $12 to $15 a pound. So if that dumpster was filled with tin, I would have gone dumpster diving, but it was really filled with steel scrap. Someone doesn't know their stuff that labeled it. Okay, so it's also used in babbitt, pewter, and solder, which we just talked about. Okay, so it's a key ingredient. I just like it because it's easily, you can use it for solder. You can use, I use it all the time. Tin is great stuff. Okay, so titanium, why do we use titanium? Well, it's got a great strength to weight ratio, but it's very, very difficult to refine titanium. Aluminum was really valued back in the old days, but they couldn't even make titanium. They didn't have a process for doing that back in the old days. So how do we make titanium? It's a whole big process. We don't actually go through how you do it, but there's a place out in the desert nearby where Henry and I do our land sailing on the Mojave Desert. It's in Arizona. I'm trying to remember which side of the border it is. And so we went there and got to get a tour of it. It's at one of the old nuclear test sites. So that's kind of off to one side. But they make titanium there, and it's really an amazing process. And now I know why titanium costs so much. It takes a huge amount of energy and effort to make titanium. So, but it's got a very, very high strength to weight ratio. It's 44% less dense than steel, and many of the alloys they're stronger than steel as well. So it can also go to really high. You saw that 3,000 degrees was the melting temperature of titanium. When you add alloys to it, it lowers it a little bit, but you can have high operating temperatures of something with titanium. It's very corrosion resistant, but it's expensive, and it's biocompatible. It doesn't corrode inside your body. It actually, a lot of times, it's used for knee and hip replacements, stuff like that. some titanium alloy. So these parts actually go inside your bone, and the bone grows into that. A buddy of mine was 3D printing some of these parts, and they would 3D print like a mesh over here on where it goes into your bone, so your bone can more easily grow into it, so that you don't have to glue it in place. What happens a lot of the times on these is that you basically cut the bone, you cut a notch in the bone here to hold that, and then they glue it in. Okay, well, if that glue fails, then they got to go back in and replace the joint. It's not a fun program. Okay, so that's titanium. Very expensive. One of the things I want to tell you about titanium is that it actually can be easily contaminated with nitrogen, oxygen, and forget what the other one is. But mostly nitrogen and oxygen are the two big ones that you can get contamination. And so if you're welding this or something like that, if you have even parts per million of oxygen, it will get a lot stronger, but it'll get brittle. So processing can be difficult. You have to do it under a really super high vacuum. Tungsten. What do we do with tungsten? Okay, well, we use it for high density applications. Okay, so you can make, I think they even make bullets out of tungsten, some parts of bullets, so that they're very, very high density. It's got a density like 20 or something like that. Lead's only, I forget, 12 or something like that. Way higher than lead. Melts at like 7,000 degrees Fahrenheit. So essentially, it can withstand really, really high temperatures more than anything else. That's why we use it for filaments in the old-fashioned light bulbs, because it can withstand those high temperatures. The other thing, it has a really high modulus elasticity. Remember at the beginning of the semester, modulus elasticity was that slope of the stress-strain diagram. Okay? So if steel's here, aluminum's down here, tungsten's way up here. It's like 50 million psi or something like that. Whereas steel is 30 and aluminum's 10. Okay? I think titanium's somewhere in between steel and aluminum. So it's really hard to manufacture though, because you can't melt the stuff. Usually it's done in a powdered method. It's also used and combined with carbon to make tungsten carbide, which is a very, very wear-resistant material, and we can combine it into using powdered metallurgy. You can make little shapes of it, and then that's what we're now using for, like, if you have a carbide blade for your saw for wood, that's a tungsten carbide. Those little teeth are tungsten carbide. So we use it for machine tools. Now, you're not using it when you do your screwdriver in the lab, because it's really hard to grind. You can't grind the shape out of it. And you can't make it quite as sharp. Tungsten carbide, you can't make quite as sharp as a high-speed steel tool bit. Remember, we talked about high-speed steel, that it can withstand much higher temperatures than most steels when you're machining with them. Okay, and the last material we're going to talk about is zinc. Now, zinc is used in a lot of stuff. Next time you go and you pump gas at the gas station, what you want to do is you want to take the little nozzle out, and you look at the nozzle. You never even looked at that thing, okay? It's a bunch of castings in a tube that comes out the end. So probably the actual handle part, that's aluminum, okay? But the fitting at the back where it swivels, and all of the couplings all the way up until, I don't know if you knew this, on a gas pump, there is a quick release mechanism. People all the time, they leave the gas nozzle in the side of the cart and they drive away. And it has this special thing on there that rips apart and keeps you from wrecking the pump. All those parts, most of them are made in Wisconsin at a company called, I think it's called Serval, and those are zinc. So all those little threads, all the little connections of that hose are zinc, and that little swivel thing, and sometimes the actual pump handle itself is a zinc die casting. But the most exciting thing that is made out of zinc die castings is Matchbox and Hot Wheels cars. Okay, so those little highly detailed castings are cast in a steel die, and the metal's injected in there. Probably, I don't know for sure, but in this cell phone here, there's probably, I don't know, 10 or 20 little bitty zinc die castings, and they'll be microscopic almost. But they'll need like a really crazy little shape, and they'll cast it in these little bitty dies. And there's lots of little stuff like doodads like that in your phone probably. Connections or some little structure inside there. What else? Old car trim emblems. Why? Because they're easily chrome plated and they can have a lot of detail. So like an old Mustang or a hood ornament from an old Oldsmobile or something like that. Those were all zinc die castings. Zinc's heavy though. It has a high density, but a similar strength to aluminum. So if you can handle the weight of it, then you're okay. But the problem is most cars nowadays can't handle the weight, so they'll go with aluminum instead or some other plastic in some cases. But you can make many parts out of a die, like 1 million parts out of a die. It's very fast. It's very cheap. It can be coated, and it can be chrome plated or whatever, but you can also use zinc to coat the steel, and it's called galvanizing. So that kind of spangled, if you look at, sometimes they're like posts, like, you know, big posts for lights for cities. You go up close to them and you can see that they have these like little crystals on the outside of them. What's the deal with that? Well, those crystals are actually the crystals of the metal that were formed when they dipped that thing into molten zinc. Okay, and they have these. Sometimes they have baths that are like 100 feet long, filled with molten zinc. So that it melts at a relatively low temperature. Let's see, pure zinc melts at what temperature here? I had it up here just a minute ago. Let's look here. So zinc melts at 787 degrees Fahrenheit. So if we had a piece of heat-treated steel, we wouldn't want to dip it in molten zinc because it's going to get rid of the heat treatment. But for most lower strength steels, we can dip it into the, in fact, they even have some kind of heat treatments you can do with the zinc that kind of anneals the steel or something like that. Yeah, that's zinc. So galvanizing. Oh, by the way, galvanizing can be done either as an electroplating process or a hot dip. Now, if we want to have long-term corrosion resistance for like a ship or something like that, or for your frame on your car, you want to do the hot dip one. If you're just taking a fastener, like when you buy a fastener from the hardware store, it's been electroplated in zinc. That's why it's shiny silver colored. Okay, so it's electroplated in zinc. It's a very thin coating, so it doesn't last for very long. So if you have that thing in an outside, it's only like 1,000th or something thick. So if you put that in an outdoor environment, that eventually will go away relatively quickly. So what's going to happen when you have zinc plated on something is the zinc is going to primarily corrode first. And when all the zinc is gone, then the actual iron will corrode, or steel, or whatever it is. So if you see a barn, the roof on a barn, you know, you see these big panels on, and they start to rust or whatever. Okay, well, it's a certain, they're all rusting at the same time and probably in the same place, and they're, you know, on each panel. And the deal is that particular plate had a certain thickness of zinc on it, and it's gone now, and now the iron can corrode itself. One of my Land Rovers has a galvanized frame. They only did that in South Africa. And so I actually have a galvanized frame, so that the frame is in perfect condition. The car is 27 years old now, and it's pretty cool. A little bit of light white powder on the surface from the corrosion of the zinc, but it's thick enough that I probably have another, I don't know, 20, 30 years, which is all I'm going to need out of it. So that is the end of the materials that we're going to talk about, the different types of steel and aluminum and that kind of thing. And so study through all those sections. The first test usually goes up into it, includes this chapter. And so now you have all the lecture that you need to do test number 1 in this class. So go back and read the stuff in the book, answer the quiz questions, and study up. So that's it for this lecture.